This is it's fine?
Yeah.
Or a bit upper? Okay, perfect.
It was not a postdoc, or was it a visitor?
Yeah, while I was postdoc in Tokyo. Yeah, and I could supervise some students because at the institute they didn't have any astrophysics, so I could supervise a student on machine learning applied to astrophysical, to three-body problem basically. And then I moved 1 year and a half ago to Europe with a Marie Curie fellowship to the Niels Bohr Institute, where I'm part of the gravitational wave, astro-gravitational wave group.
Until when?
Until Marie Curie fellowship ends next April, then I can extend 1 more year basically. Yeah. And scientifically speaking, these are my main interests. I touch many topics throughout my career, and starting first was star cluster dynamics, then moving to galactic center science, which means modeling the orbits of the stars close to the supermassive black hole, also gas and stars close to Sagittarius star at the center of the galaxy. It's a very crowded and dense environment where there are a lot of kind of peculiar observations that need to be addressed with some formation models. And then after moving to University of Tokyo, I started focusing more on few-body problems, few-body dynamics applied to mainly 3 different topics, exoplanet and exomoons. I did some work on migrating exoplanets, and I work in collaboration with people that do transits to characterize the dynamical stability of observed exoplanetary systems. Nowadays, I do very limited work in exoplanets. I collaborate with these observers mostly. Because most of my time is spent in the studying information evolution of gravitational wave sources. This is this last seminar I gave online, and I'm particularly interested in the new AGN formation scenario, which is very hot topic nowadays, and it might change the way we understand the AGN ecosystem by
What's this?
AGN, active galactic nuclei. Yeah, there's accretion disk in the center of galaxies. And but today's talk is more about more kind of theoretical problem, is about chaos and statistical escape theories of the three-body problem. This is usually a topic I don't bring to astronomical departments because they're more research in the gravitational wave sources formation, but hope you'll find it interesting anyway. And also it has some, it's not just an academic exercise, it has some implication for astrophysical models I will show at the end. So the three-body problem has many applications in astrophysics, starting from exoplanetary architectures. The modeling, the origin of gravitational wave sources in the 70s was basically studied because of there is a key component of the evolution of stellar clusters, where in the inner region you have these kind of encounters which kind of power the energy, the kinetic energy flux at the center of these clusters. And of course also to stellar multiples. So many stars come in multiple, including the closest stars to the sun. They are in a triple system, Proxima Centauri. And yeah, but has, of course, has a much longer history, tracing back to Newton. Many mathematicians applied it to the lunar problem, the lunar precession problem, how to explain the precession of the lunar perigee. And eventually, it just was Poincaré that kind of demonstrated the non-integrability of the three-body problem, and this opened the way to many branches of mathematical physics.
I don't even know what integrability is. What is non-integrability?
Oh, in the sense that there are no that you don't have all the full integrable. You cannot decompose it in all action angle variables. The Hamiltonian cannot be decomposed in action angle variables. It doesn't have enough constant. Doesn't have enough constants of motions to be fully integrable.
Yeah, but you didn't tell me what fully integrable is.
So in the mathematical sense, it means that you can, all the coordinates of your Hamiltonian can be expressed as a couple of a constant of motion and an angle, and the dynamics is fully regular and smooth in this what the Kamptori. Yeah. And so, but most of the problems that were studied in the century were like applied to the hierarchical triple systems. While what I will focus on is non-hierarchical triples. So the hierarchical triples, like the Moon, they are stable systems. So in the sense that there's a fixed hierarchy. In the case of the Sun and the Earth and the Moon is also hierarchy masses, but can be just in space, just stellar triples. And non-hierarchical triples we originally called three-body encounters in astrophysical system, and they were first studied exactly when.
Sorry,
Oh, these are trajectories of.
previous.
Okay.
I mean, what do you mean by one
Yes.
imply the other and the other?
So generally speaking, you go a metastable hierarchical triple will become non-hierarchical, will disrupt.
I see.
Let's say if you put the Moon a bit farther out from the Sun, then from the Earth, will become unstable, and then will become non-hierarchical. But the opposite is impossible. It's not impossible; it's unlikely. It's a way you can see it as a way that you increase the entropy of the system by going from the hierarchical state to the non-hierarchical.
But in this case, if ideally, I guess, you would be able to solve the non-hierarchical, the hierarchical would be just a simple case of that, right? No.
They're
They're not integrable, so you
not integrable. Yeah.
But I would guess that it's more complicated to solve the non-hierarchical.
Yes. Yeah, the hierarchical can be integrable, so it has an analytic solution, but only in a very limited specific condition. So, and the full.
You say is analytically solvable, but still not in terms of action angle, because Poincare shows. Okay.
No, it is analytically, so it has a full solution.
No, but
Not.
because this is always something that I
Yeah.
a little bit fail to understand.
Yeah.
In principle, saying that the system is integrable in the sense I can solve or I cannot solve,
Yeah.
by definition is a time-dependent concept. I mean, it's possible that in 20 years somebody comes with
It finds the last integral or more. Yeah, integral. Yeah, okay. Yeah.
no, wait, so I misunderstand.
What?
Wait. You mean that Poincare showed that there are no enough integral motions or couldn't find the action angle variables, but there might be different
He didn't really think in terms of action angle variables.
So what did it show?
He showed that if you expand the Hamiltonian in a series which represent the various harmonic frequencies, it's called Lindstedt series, and the solution of which is basically you can predict what is the precession of this series does not converge, and this maps directly to the not existence of Cantor, yes, yeah, to the integral
That
field.
implies that there are no enough integral of motions, I guess, right?
Yes.
Okay, so finding an analytical solution means that you have, like, let's say, Ramanujan style, you have a dream in the night, and you come up with a solution.
Yeah.
Okay.
Yeah. And so if you think about in terms of equations of motion, they're time symmetric, if in the Newtonian case. So there is in principle, you're not forbidden to go to one state to another, right? But just the fact.
The usual, let's say, statistical mechanical.
Exactly. Yeah. So just the fact that you're going from one system to another, it tells you that this is not actually a stable system. Okay.
But did you say that the hierarchical triples are solvable? Exactly.
Yeah. Okay. So it's a lot of approximations. So basically, you take the Hamiltonian of the system in relative coordinates.
In some approximations, yes, but
In some approximation.
in principle, it's not.
No, in principle it's not. The full problem, no.
Because it's triple.
Yeah, exactly. No. So first, so if you,
That's why the solar system, take the solar system.
it's definitely and it's not in.
It's very stable.
Yeah.
But actually,
It's not exactly.
The time scale for the chaotic behavior of the solar system is, I don't know, billions of years. I don't know.
Yeah, it's a few million years actually. It's because it was done by Jacques Lascar. It's basically because Mercury, Jacques Lascar. Yes.
It was
Numerical calculations.
20 years ago.
Yeah. He found out that the system has a very short Lyapunov timescale, maybe, or stability timescale. because of Mercury orbit is very chaotic and might increase in eccentricity and basically intersect Venus. But the full idea of the kind of only integral analytical solution of the three-body problem in the hierarchical sense is when you assume that there is no energy you exchange between inner and outer orbit. So all you remains in your Hamiltonian is the interaction term in angular momentum between the inner and outer orbits. Though that one you expand to the quadrupole level, and then you orbit average, and that's integrable. If you already expand to the octupole, expansion in semi-major axis, ratio semi-major axis is already not integral. No. And this is very complicated, and I'll show you here integration. So this is how the three-body encounter looks like in Newtonian physics. There was a binary coming from the left and a single from the right. You see the evolution looks very, very chaotic, and I'll show you again. But we can make some basic observations about the evolution of such a system. So the first one, there are some moments in time where all particles are in the same box, in the same region of space, and freely exchange angular momentum and energy. There are some states in which we have an excursion. So you have a temporary binary that forms a single that recoils that are temporarily separated, but they're going to come back. And finally, the end state of this system is a breakup again. So you end up with a binary in a single on hyperbolic orbits, divergent, so they're not going to come back again. And
binary and single, or it can be three singles then?
Yes, but depends on if the total energy of the system is positive. Yes, you can have three singles. In this case, so all this kind of theory is based on the fact that the system is bound. I mean, the negative total energy. Yes. So there are some better ways to solve the problem in a statistical sense, just by considering these two facts. So we can decompose the system into these kind of states: democratic interactions, which mix the phase space of the three-body problem by exchanging energy angular momentum, and excursions, where the system is separated. And I'm ignoring here this kind of special mathematical solution called braids or choreographies. One famous one is the figure of 8. They do exist. They are, for example, this is non-hierarchical stable solution of the three-body problem, zero angular momentum as well. Astrophysically speaking, they're not very relevant. Although Douglas Heggie, by perturbing this configuration until it breaks up, and so calculating what is the impact, the cross-section, if you do the reverse integration of this interaction, he calculated what is the possibility in the galaxy, in the universe, to form a relatively long-lived figure of 8. And the probability is like you can have one in the galaxy or one in the universe, so it's very small. And so the main idea to solve this problem not besides just brute force is using statistical escape theories, so using tools of statistical mechanics.
Figure 8, they all have to have equal mass or not?
They have to have equal mass, but there are some choreography with unequal masses. Yeah. And so the main idea was started by statistical physicist Monaghan from Monash University, and the main idea is that to leverage chaos as a agent that mixes completely the phase space, so that we can imagine that as a function of time, let's say, if this is the phase space of the three-body problem, the system, given enough time, will uniformly populate this space. And then the system will...
That's called the ergodic system?
Exactly, yes, ergodicity, yes. So the main idea is to apply the ergodic principle. So instead of doing this kind of time average, we do ensemble average, and we sample the accessible phase space of the three-body problem. And by accessible phase space, it means that we need to imagine that at some point the system will disintegrate or decay, and we can put ourselves in the system, in the relative frame at the moment of disintegration. So let's say you have the binary here and the single here, and you use relative coordinates to kind of map and characterize the phase space. So you're in terms of
the statistical method assumes that the system is ergodic.
yes, it assumes that the system is ergodic. Yes.
But you just showed the figures in phase space. This one that is
Yeah.
calculating there is not ergodic. So
Yeah. Yeah, exactly. Yes. You know, it's not fully ergodic. Yes, there is mixed.
this is a very small island in the full phase space. The idea is that probably
It's actually the ergodic phase space is actually the majority of the phase.
Exactly.
Yes.
Exactly. I would say
Yeah.
the cases that are not. I mean,
No,
I
no,
have in mind
yeah, no.
something
If
like
you
the Poincaré section.
if you think about the choreographies, yes, they are basically measure zero.
Exactly.
Yes, but there are also regular orbits that are not ergodic. Yes, there are some trajectories that are not chaotic or yeah. I mean, there's some phase, yes, and yes. So by applying the ergodic principle, all one needs to do is to characterize what is the phase space of the Triboli problem at the moment of disintegration, and it boils down to computing this integral where you take into account that there are some constraints. So the first constraint is the energy conservation. So the kinetic energy of the outgoing single and the orbital energy of the foreign binaries in the reference frame where the binary is at rest needs to conserve. So there is a E0 minus EB minus ES needs to conserve, and then you add this delta function to the integral. Then you can do the same for the angular momentum. And originally, the paper of Monaghan only considered energy conservation, for example. And then after going from say this canonical coordinate to some other more convenient called Delaunay coordinates, they're kind of closely related to the orbital parameters. That you can consider this as a hierarchical triple where the outer orbit is hyperbolic. Eventually, by developing this integral, you can obtain, and this was obtained only in recent years. This was obtained only in recent years, in 2019, a full expression, analytic expression for the outcome states of the Triboli problem. So what you do here is to add. Yes, so sigma is your phase space. Is your integral. Is the volume of the phase space. Yes. With these constraints of conservation of angular momentum, conservation of energy, and there is a third constraint that is causality. So, for example, if you have a single coming from here, and your binary is here, so you can see that if you trace back the orbit of the single, they don't seem to be causally connected. So the theory has a kind of arbitrary variable that is the interaction radius, and given usually is taken as a multiple of the binary, say, major axis, or a multiple of the binary apocenter, yes. So 1 plus E, yes. So it's the apocenter of the binary. So this is arbitrary. K can be usually taken to be 5, but one has to define this interaction radius to remove these non-causally connected trajectories, and to, in a sense, regularize the phase space volume. And for example, here I traced the trajectory as straight line. Originally, in the original paper by Monaghan, he only considered straight lines, while in this last paper includes also treatment of hyperbolic orbits, so which makes more sense from a physical point of view.
I'm confused the notion of causality in Newtonian gravity, because in Newtonian gravity there's no causality.
Yeah, well, it's No, there is no causality because of time symmetry of the equation of motion, but in a sense, what we are interested is to characterize the phase space volume in a region of the phase space where you can have a disintegration. I mean, these two orbits from the Newtonian point of view would make sense, but they definitely, if you were to propagate in time and backwards, you will see that they are not actually interacting. They are just, you could see them as a flyby, for example, a flyby between a binary and a single, but this is not a chaotic interaction.
Yeah, just worried about use of the word causality.
Okay.
In fact, this is not an exact statement, as you said. This K is not determined. So
No, it's not. It's a flaw.
It's not an exact statement of causality.
No. Okay. I see.
It's wave hanging, if you're hanging your wave.
I see. Okay.
Because you don't know exactly what this thing is. So you're putting it. It's a how to say.
You're putting a cutoff in the interaction in a sense, right? You see beyond the distance, they don't talk to each other.
So they always talk to each other because gravity is infinite range. So it's a kind of effective thing which it.
Yeah, no, I see. I should be more careful with calling this causally connected, right? Because it's more of a way to remove non-regular orbits, yes, and non-chaotic orbits. Yeah, that's probably what should be said. So eventually, what you have in the end is this expression. You can integrate over angles that they are supposed to be uniform. For example, the mean anomaly of the boundary doesn't enter this expression because it's been already integrated out.
So this expression depends on R, capital R.
Yes, there is a capital R. That's it. That's one. Yeah.
Which is a free parameter.
It's a free parameter. Yes, which depends also on the orbital parameters of the binary. So but it has K. K is the free parameter. Yes. Inside. But one can take this expression and marginalize it, and this is going to be our outcome state probabilities. So here, for example, I marginalize this the integrand over say major axis. Well, here you don't see, but it's basically is EB.
Marginalizing is integrating over, right? That's what you mean by marginalize is integrating over.
Yes. Integrating over because this is a trivariate distribution. Yeah. So the key point is that this is a trivariate distribution. Eventually, the integrand is a trivariate distribution for binary energy, final binary energy, or say major axis. Let's say final angular momentum, yes, or eccentricity, and the angle. So here is called CB, I think. CB, yes. But what this is basically this binary will have an angular momentum. Let's say, and this binary angular momentum. No, it's LB. Will have an angle. Will have a direction with respect to the initial the total angular momentum. So this is all. There is basically let's say the angle between the final binary or the ejection direction of the single and the original angular momentum. And this fully characterizes the problem, because then with given masses and total energy and total angular momentum, you have all the properties of these final binaries. And here, yes, I integrate over the angle and also over the energy, and find that given certain masses and total energy and total angular momentum, you expect these distributions.
Sorry, it was a bit fast for me.
Sorry.
I don't understand how the concept of probability appears from the volume of the phase.
Oh, it's basically it's part of the ergodic principle, in the sense that rather than we are assuming that the system populates in time the full phase space. So eventually we'll disintegrate from any given point in time in this phase space. So this phase space is proportional to the outcome probabilities. That's the main assumption.
Less than 1 minutes?
Yeah. Given all these constraints, it becomes it becomes finite. Yes, yeah. Given mainly this, it is less than, it is finite. Yes, does not diverge. Yes.
Derived analytic? It's just. How did you get these probabilities? And why can't machine learning?
The probability, for example, is for example, if you want the probability for.
No, I'm asking a different question.
Oh.
It looks like you have analytic expressions, right?
Yes. From
why
the.
can't you just use machine learning and do it much more accurately?
No. So machine learning. So I collaborate with people who try to predict the Triboli problem using machine learning, and it doesn't work very well because it's chaotic. Yeah, because exactly.
It's chaotic. Why does that work well?
Because it kind of uses chaos as well. It depends. Well, you're right. So it depends how you want to solve it. So what some people have tried to do is to, given an initial set of initial condition, predict deterministically what is the final outcome state. Yes, just by. Yes, exactly. It doesn't work because the system is chaotic. They did try. Yes, and to really predict the trajectory of individual. Yes. People try many things.
I'm asking the question: why should this analytic expression be more accurate than machine learning? That's what I'm trying to ask.
But there is no machine learning attempt so far. There's nobody has an attempt to really solve with machine learning the Triboli problem as a statistical problem. So rather than
That's what machine learning does. Put in billions and billions of samples, and then that tells you.
But they are completely unpredictable. I mean, you change a little bit the initial condition.
No, but then the analytic expression is useless also.
The analytical expression, I think, is useful.
It's useful to have fast predictions on the states of the Triboli problem, and machine learning. I mean, also
When
you.
I say machine learning, I just mean you just throw in all these. You just let the things propagate, and then you just average over all the answers. Because you're going to average at the end anyway. So why do you care if the average comes from some analytic or from some just numerical simulation? Who cares?
Well, so I don't think anybody ever tried to use machine learning to solve exactly the same problem. So rather than solving individual orbits, try to use machine learning to map this trivariate distribution.
I don't know anything about machine learning. I just mean you do numerical simulations from a million of them.
Yes.
And then you just average over the answers.
Yes. Yeah. No. That's what we do to compare the theory with simulations. The problem is the parameter space is huge.
Machine learning is good at it.
Yes, brute force. Okay. Brute force integration is still very expensive numerically.
Okay.
It's
Okay, maybe it's just too expensive. Okay.
yeah. So.
Maybe another related to what I mean, from this analytical formula, beyond predicting the plots, can you extract also some lesson about, let's say, the formula themselves carry some information that would answer a little bit, because the machine learning provide, if you want, the plot, the average plot, but you absolutely don't know
what's in the box.
The machine has learned.
Yeah. Okay.
Maybe from that formula there is some lesson that we can get that goes beyond.
There are some. You can analyze the function, find some asymptotic behavior, and that connects to the kind of equilibria of binaries, binary same energies in stellar cluster, assuming that they continuously interact. The two things, the asymptotic behavior of this function for EB maps directly to those calculations of statistical mechanics, but besides.
So you say
mostly
this
no.
formula
No.
is used to spit out.
To spit out a probability. Yeah. And by the way, there is.
Why the probability is bigger for one eccentricity equals to 1? Is there an explanation why the system prefers to be in this state?
So usually what we call this kind of similar eccentricity is not exactly this one because it's thermal eccentricity. It's distribution function is, so this is again comes out of statistical calculations of assuming that you have binaries that interact in a uniform medium with isotropic, maybe Maxwellian and velocity distribution. Eventually, in those calculations, you should have find that the binary distribution of, say, major axis settles into this thermal distribution. And we call it thermal, exactly because it's expected from a binary that continuously interact with single stars so it thermalizes, basically. It's not exactly the same because it's not exactly the same calculation. So, yes, it's an equilibrium, but only in this very specific case. Yeah. And why the physical meaning is, well, it's still close to a thermal distribution. It should be straight. That's basically, say, a state of a uniform state that the system tends to, an equilibrium that the system tends to, which is slightly perturbed. It's not exactly this thermal, but it's close to it. And, well, it relates to the total angular momentum, basically. If you take this function and you bring the total angular momentum to 0, which you can do, you can have a 0 angular momentum triple. You just have, for example, the binary has points this way and a single points this way. You'll see that this function actually that function will become highly peak at 1. The reason for this, the physical reason, is that there is not enough angular momentum to be redistributed between the binary and the single. So we call the outcome distribution superthermal. And this is very important for many physical processes that require high eccentricity, so close pericenter passage, gravitational waves, or stellar merger, and so on. I wanted to show you this plot here. This is the distribution of this lifetime of stellar triples. This is given, so different colors are actually different mass combination of masses. And you see that it's basically, they all get down to a power law. So if we were actually to assume that the system simply decays in a stochastic process from this phase space, we should naively expect an exponential function. Exponential decay, like in the atom. So the reason why we have a power law instead is due to the fact that we have this.
Sorry, I missed what was the power law. So what is N?
Oh, power law is so this is a log. So this is a log. So the